Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 3, part of this playlist that I'm calling Continuous Random Variables. And today's topic is the normal distribution. Let x be a normal random variable with parameters mu and sigma squared. Then the density for x is given by this expression. F of x, given the parameters mu and sigma squared, is equal to 1 over the square root of 2 pi times sigma times e raised to the minus 1/2 x minus mu over sigma quantity squared. Let y be a standard normal random variable and let x equal sigma times y plus mu. Then x has a normal distribution with parameters mu and sigma. Now we're going to use a technique that we proved in an earlier video, that if you know the CDF of a function, you can take the derivative to obtain the density function. So let's first drive the CDF of x. So f of x is equal to the probability that a random variable is less than or equal to some value, little x. Let's plug in what we are defining as x, which is sigma y plus mu. Solve for y. Well, the random variable y is a standard normal random variable, and this is the probability it's less than or equal to some value, which is the CDF. We define that to be capital Phi of mu x minus mu over sigma, right? This value. So this is it. This is the CDF. Now let's take the derivative of this. Next, take the derivative of f of x to obtain the density of x, little f. So the derivative of capital F is the derivative of this. So this is capital Phi, which is a CDF. So that becomes the standard normal density evaluated at x minus mu over sigma. But we also have the chain rule that we have to pay attention to, and this is the derivative with respect to x. So the chain rule gets us 1 over sigma. Now let's plug this value in for the standard normal density, which is this, we put it in squared, right? This is it. Well, this is the standard normal density, not the standard normal. This is the normal density that we defined up here. So we've proved that defining x as sigma y time plus mu has a normal distribution. Now let x be a normal random variable with parameters mu and sigma squared. Then the mean and variance of x are given by this. The mean is mu and the variance is sigma squared. Let y be a standard normal random variable. Then x can be represented as x equal to sigma y plus mu. So to find the expected value of x, then we plug in what it can be defined as. They're equivalent expressions. Expectation is a linear operator. So the only variable is y, the others are constants. The expected value of a standard normal random variable is 0, so it leaves mu, and that's what we wanted to show. The variance of x, then we plug in sigma y plus mu. Constants, adding a constant doesn't change the variance, so that can be taken out. Constant times the variable comes out squared. The variance of a standard normal random variable is 1, so that leaves sigma squared, and that's what we wanted to show. Now let x be a normal random variable with parameters mu and sigma squared. Then the moment generating function of x is given by this expression. The expected value of e to the tx, that's the definition of a moment generating function. And we're saying it's e raised to the mu t plus sigma squared t squared over 2. Now we're going to use theorem 5 from video ims33. This stands for the 15th video in the playlist Introduction to Mathematical Statistics, and that's on the moment generating function. And it's in regards to defining a random variable as a linear combination of other variables. So the moment generating function of x, by definition is expected value of e to the tx. But since x is defined this way, theorem 5 says that we take the constant, and it's e to the mu t. We stick that constant here. Then it's the moment generating function of y, this variable, but we plug in sigma t. Well, e to the mu t comes over. The moment generated function for a standard normal random variable is e to the t squared over 2, but we plug in sigma t and we get this, combine the e's, and that's what we wanted to show. So we've proved the theorem. Now calculating probability in a normal distribution. Let x be a normal random variable with parameters mu and sigma squared. And we want to calculate the probability that x is between a and b. Now, first of all, using a computer is easiest, bar none. However, if you must use a standard normal CDF table in the back of a book, use this approach. So the probability that x is between a and b is integrating the density from a to b. And this is the density of a normal distribution. Let's do a change of variable, y equal to x minus mu over sigma, this piece here. Now don't forget about the Jacobian, which is the derivative of this. So it's, well, we'll do it. So when the derivative of this is 1 over sigma. So dy is equal to dx over sigma. I'm going to let you do that step. But then we plug in y here. And this sigma and dx is dy. 1 over the square root of 2 pi comes down. And then we plug in the values of integration. Well, this here is a standard normal density. We're integrating it between two values. And we showed in an earlier video to calculate probability in a standard normal distribution is the difference of the CDFs. And we plug in these values that we're integrating from. And this is it. So this is the probability. Then we can look this up in the back of the book and come up with two numbers, subtract them, and we have it. Now let's do an R illustration of this. We're going to integrate or find the probability that x is between 2 and 6. So a is 2 and b is 6. We're going to let the normal distribution have a mean of 4 and a variance of 4. That means a sigma or a standard deviation of 2. And the reason I do that is because the function in R, it asks for a standard deviation, not a variance. So to take the difference of the CDF, so we want the CDF at B minus the CDF of A, and P norm is the CDF function. And we're telling that this is a normal distribution with mean mu and standard deviation sigma in both cases. And we get 0.682, blah, etc. Now, if we were to transform these to a standard normal distribution, we would take B minus mu over sigma, and that's the CDF of a standard normal, so that's a mean 0, standard deviation of 1, minus A minus mu over sigma, standard normal distribution. The difference of those CDFs is the same, 6.82, etc. Now, let's do a graphic or illustration of what's going on here. Now, the R code is not as important as the graph, so I'm going to skip that, but as always, I will copy and paste it into the comments section. So the top represents the original normal distribution with a mean of 4 and a standard deviation of 2. And we want to calculate the probability of being between 2 and 6. And what we do is we map those down into the standard normal distribution, has a mean of 0 and a standard deviation of 1, using this formula here. And that's a linear transformation. And it is unique. So we're mapping values in this real number line to another real number line. And I'd point you back to when we were looking at the standard normal curve, when we mapped the real number line into the line segment from 0 to 1. It's possible. You just take this linear transformation and it works. Okay, well, that's all I have for this video. We're right about 10 minutes. The next video will be on the beta distribution. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.